Our next speaker is Stoeckl, and we'll be talking about a Koszul operad governing wheeled props and one for props as well. Take it away, Kurt.
Okay, so it's been known for a pretty long time that there exists operads governing operatic structures. And if you don't know what either of those two things are, then a good way to think about this is that there exist trees governing how we can form different, more general graphs. So a pretty general way to describe operads governing operatic structures is given as follows. If we have some set of graphs that satisfy some properties, we say that a graph is colored if each of the flags or half edges of the graph have some color from some non-empty set of colors. And this is subject to the condition that if any of these flags or half edges are joined together to form an edge, that these flags or half edges must have the same color. So our edges have one color. We say that the graph is ordered if the vertices of the graph are ordered. So V1 is smaller than V2 and so on. We say the graph is directed if each of the vertices have inputs and outputs. And throughout this talk, I'm going to put the inputs of any vertex at the bottom of the page and the outputs at the top. And ordering the inputs and output of the vertices orders the inputs and outputs of the graph. Finally, we say that these graphs are wheeled if there may be directed cycles present in the graph. And an example of a wheel is given in the second graph on this page here. Here, in this second graph, one of the output flags of the first vertex loops back around and connects to one of the input flags, forming a wheel or a directed cycle. So given we have these sets of graphs, we can associate an operatic structure to these sets of graphs. So one way to do this is via a partial composition. So if we have two graphs in which the profile of the second graph, which is to say all of the inputs and all of the outputs, matches the profile of one of the vertices. So this first vertex has the exact same inputs and outputs as the entire second graph. And then we can substitute the entire second graph into the vertex of the first graph, yielding some new composite graph.
Do your edges have colors even if they're not even if they're not open?
Yes. So just to clarify a question of Chris, that the flags are colored, and if the flags are connected to form an edge, then they're both colored and they both have the same color. So
one thing is like that. So C1 is coming out of.
Pardon, sorry.
Right. So in the first picture, you have like one thing you found it that you can see in the things and giving right.
Sorry.
Okay, never mind. I can ask later.
Oh yeah, sorry. I'll be a little hand wavy on the details here. But the idea is that if we flesh out this example into a full partial composition, then this defines something called a colored operad in the category of sets. And if we're interested in other symmetric monoidal categories, then we can enrich this operad in sets into an operad in other symmetric monoidal categories. And a fact I'll just claim is that algebras over this enriched operads are something called a wheeled prop in that symmetric monoidal category. And I'll define what a wheeled prop is later. So another way to say that algebras over this operad are wheeled props is to say that the operad governs wheeled props. And again, if you don't know what an algebra over an operad is, then there's a nice analogy that says that group representations are to groups as algebras over operads are to operads, to give a vague intuition of what's going on. So a slight variant of this problem of constructing operads governing operads is to instead construct an operad which satisfies a further nice property of being Koszul. I'm not going to define what it means to be Koszul, but one application of this operad governing modular operads being Koszul is that this provides a model of an infinity modular operad, and so on for all these other operatic structures. And we know that there exists Koszul operads for a bunch of operatic structures, but two notable exceptions that haven't yet been worked out are props and wheeled props. So today I'm hoping to talk about how we can construct a Koszul groupoid colored operad governing wheeled props. And I'm going to do this by starting off with a certain definition of a wheeled prop. And then I'm going to show that we can use this definition to induce a definition of the operad governing wheeled props, which is, it's almost going to be the right definition in that it has some nice, it has mostly quadratic relations, but there's going to be a few problem relations that we're going to remove by moving to an isomorphic groupoid colored operad. And then finally, I'm going to discuss how we can prove that that groupoid colored operad is Koszul. So now for some preliminaries. Suppose we have some non-empty set of colors, and we can consider sequences of colors from that set. We can then define this category PC to be the category whose objects are just these sequences of colors. And the morphisms are permutations acting on these sequences of colors from the left. Given we've defined this category, we can then define this product category, PCOP times PC. And because all permutations are invertible, this category is going to be a groupoid. And this product category is important for two reasons. It's going to wind up being the groupoid that we're going to use to color our groupoid colored operads. And we also need it to define something called a bimodule, which is one of the ingredients of a wheeled prop. So a bimodule is a functor from this product category to some other symmetric monoidal category E. And a good way to think about this is you've got some collection of operations with inputs colored by C and outputs colored by D, in which we can permute the inputs from the right via a permutation, and in which we can permute the outputs from the left via a permutation. And the set of graphs that we saw on the first page is actually an example of a bimodule. If you have any graph with inputs and outputs, then you can just permute the inputs and you can permute the outputs. So a wheeled prop is just this underlying bimodule with two further compositions. A horizontal composition, which takes two operations and places them side by side, forming a new operation with all of the inputs of the components and all of the outputs of the components. And the contraction operator is an operator which takes an operation and it connects the ith output of that operation, loops it back around and joins it to the jth input. And as an example of the wheeled prop, again, we can consider the underlying bimodule being these sets of graphs, and an example of a horizontal composition and a contraction on graphs is given below. In the first example, we're horizontally composing two fairly trivial graphs, which are just vertices with some output flags, forming a new graph with two vertices in which we've adjusted the order of the second graph in the obvious way. And in the second example, we've got a graph with an output flag and an input flag of the same color, and we've simply contracted them together to form a graph with a single edge. No, you can only contract the same color. So all edges must be the same color. So we're going to actually want a slight alternate version of this definition, which consists of the exact same bimodule, but we're going to alter the compositions to some new extended compositions. These extended compositions are defined to be the compositions of the previous page, followed by an action of the bimodule. So we place two graphs side by side, and then we permute them for the horizontal composition, and a similar thing for the contraction operation. It's straightforward to see that this alternate definition is equivalent because this action of the bimodule was always present in the previous definition. We've just expanded our set of generators and increased the number of operations we can generate via a single extended composition. That's the idea. This accomplishes the following thing. In essence, all of the axioms satisfied via this new definition are quadratic, except for the ones written down on this page. And we can interpret these axioms as follows. The top right compatibility conditions say that if we follow our extended compositions via an action of the bimodule, then that's just equivalent to some extended composition. And the left compatibility conditions are saying that if we precede extended compositions by some actions of the bimodule, then this is just again equivalent to some extended composition. I will give an example of each of these actions. There's also an action of the symmetric group S2 on the horizontal composition, which I won't discuss today. But the fact is that every other axiom of this wheeled prop is quadratic. So this says that if we could somehow eliminate these non-quadratic relations on the page here, then we could use this definition to induce a definition of a quadratic operad governing wheeled props. So we're going to eliminate these relations by moving to a groupoid colored operad. But I need to define what a groupoid colored operad is. So this is an awful slide, but the idea is as follows. A groupoid colored module, again, has operations with inputs and outputs. We can still permute the inputs and permute the outputs, but we can now extend the input y's and the output y's via isomorphisms of the groupoid. So we have some underlying groupoid B, and we're just extending those y's. Example shortly. We can use this to define a groupoid colored operad, and one such definition is given via a non-unital partial groupoid colored operad. It consists of a groupoid colored module, which is a bimodule in which all of our operations only have a single output. It consists of a partial composition, which connects the ith input of the first operation and loops it back around to the sole and connects it to the sole output of the second operation, forming some new tree. It satisfies the standard vertical and horizontal associativity axioms of the operad and a new equivariance axiom. The most interesting behavior of this equivariance axiom can actually be unpacked as a particular case. So here, we've repeated the exact same equivariance axiom at the top of the page. And a particular case of this equivariance axiom is as follows. The bottom left path takes two operations and connects the sole output of the second operation to the ith input of the first, and is then the identity on the bottom. The path on the top extends the ith input and the sole output via isomorphisms of the groupoid, and then it contracts those extended y's. And because this is a groupoid colored operad, this composition is only defined if they're the same color. So this tells us that our isomorphisms G and Fi must meet at some new color C prime I. So G is extending the sole output of Ci to some new color C prime I, and Fi is extending the sole input over here via an isomorphism and then back to Ci. So because this is a groupoid, this composite is an element of the automorphisms of this color. So what this is really telling us is that our groupoid colored operad has an action of the automorphism groups of our color has an action on the internal edges of our groupoid colored operad. And I'll provide an example. So with this whole super painful setup, we can define the operad governing wheeled props. And this new presentation of the operad governing wheeled props is isomorphic to the original definition that I vaguely described on the first slide. And this operad has this presentation here. Its underlying groupoid is the product category that we saw earlier. Its generators of the groupoid colored module are given via the extended compositions, and the necessary actions of the groupoid on these modules are given via the left and right compatibility conditions and the action of S2. And then finally, these relations G, which I'll discuss in a bit, are given by the quadratic axioms. But before we get to the axioms, here's a nice example. Suppose we have these two graphs here. We can feed these two graphs into an extended horizontal composition. This places the two graphs side by side, and then it permutes the inputs via 2, 3, 1, and the outputs via 2, 1, 3. We can then feed this entire graph into a contraction operator, and this contraction operator takes the third output of the graph and connects it to the second input, both of which have the same color, C3, and this forms this new graph here. By inspection, it looks like there should be multiple ways to form this graph. And this is indeed the case. Not only can we form this graph via these two extended compositions, we can also form them this alternate way, where we do an extended horizontal composition with just the identity permutations. We just place the graphs side by side. If we want to form this edge, we are then forced to do this contraction 3-3. And then if we want to match the permutations of the inputs and the outputs, we are forced to make the permutation 2-1-2-1. So ideally, if we've chosen a good definition of a group wood-colored operad, these two tree monomials describing how to form this graph should be related. And this is indeed the case. The internal edge of this tree on the left has this particular color. An automorphism of P, which is pretty important, is the identity. We can split the identity as a permutation followed by an inverse. And using the equivariance axiom and the left and right compatibility actions, this describes how we can move between this left tree and the right tree. But mechanically, all we've done is we've used the action of the groupoid to push a permutation which was lower in the tree all the way to the top. And we can exploit this trick for any groupoid colored tree monomial. We can produce a canonical element of every equivalence class where we push the permutations all the way to the top. And what this enables us to do is to describe the relations satisfied by this operad in a very succinct manner. So here are the relations, and I'll explain the notation of this table. In the second row, we have a diagram representing a graph with two vertices, and in which there's one of the output flags of the first vertex is looped back around to connect to one of the input flags. We use a suppressed notation where any other flags of this graph are just suppressed, and they could have any arbitrary order or permutations. We then take these groupoid colored tree monomials on the right under the implicit understanding that they form this graph. And we again use a suppressed notation where these binary forks correspond to extended horizontal compositions, and the straight unary edges correspond to contractions. So because we can always push the permutations to the top, the graph uniquely specifies the necessary contractions and the necessary permutations. So here, in order to form this particular edge, we are forced to use certain contraction indices at this point here. And in order to match any permutation of the flags in this graph, we are forced to apply a certain permutation at the top. So this enables us to present the relations of this operad in a really succinct manner. And one way to interpret the relations is we have some associativity condition on horizontal composition. We have a compatibility relation between the contraction and the horizontal composition. And we have some final conditions that say when we can commute two contractions. So this is the underlying presentation of the operad. To show that it's Koszul, we make use of the following theorem. I won't go into the details of this result, but it's basically saying that if we have some groupoid colored operad for which the underlying automorphism groups of the groupoid is finite, then we can construct some other associated structure, which is called a groupoid colored shuffle operad. And if this associated structure admits a quadratic Grobner basis, then the original operad is Koszul. So that's the tool we use to prove the result, which is nice. So we can apply it to our particular groupoid colored operad to construct a groupoid colored shuffle operad, find it has a quadratic Grobner basis, and then this proves that our constructed operad is in fact Koszul. And again, one application of this result is that this gives a model of an infinity wheeled prop, which one potential application is this enables something called homotopy transfer theory for wheeled props. This is otherwise known as perturbation theory. And everything that I've described in this talk can also be done to produce a Koszul operad governing props with a little bit more difficulty. But thank you, that's everything I wanted to say.
Okay, any questions?
No, I think
Come up,